Good morning, everyone. My name is Katerina Chantziara, and I'm a PhD student at Karlstad University in Sweden. And I will present you our work entitled as 20 kHz cantilever bending very high cycle fatigue of high strength strip steels. So I suppose we are all familiar with the very high cycle fatigue concept, but repetition is one of the main conditions in the fatigue. So typically, we have a fatigue limit until recently to be proposed that falls into in between 10 to the 6 and 10 to the 7 number of cycles. But we know that many industrial metallic materials shows fractures to higher number of cycles. So a clarification between low cycle fatigue, high cycle fatigue, and very high cycle fatigue could be done based on the number of cycles completed. With the ultrasound 20 kHz fatigue testing setup, we are speaking about a less time-consuming method since we can achieve 10 to the 10 number of cycles in 6 days, and we can have high and very high fatigue strength in both uniaxial and bending conditions. The innovation in our work is that we use this ultrasound 20 kHz testing setup in order to test high-strength strip steels. So we can characterize the and having fatigue data about bending fatigue of different strip steels, different in thicknesses and properties. The main application of the strip steels is the flapper valve in many common devices like fridges, for example. So we have the setup here at the ultrasonic generation, an electrical signal it is produced, and through the booster and the magnification horn travels to the specimen as an oscillating vibration. It is a displacement control loading, while the displacement amplitude at the bottom of the horn is calibrated against the voltage input. We use the FEM calculations in order to have an image about the stresses. My colleague presented detailed these results, while the specimen is designed to have a resonant frequency compatible to the load train, and also to be sure that we are in the mode 2 flexural bending conditions. So in that table, you can see the 4 tested grades, A, B, C, and D, the chemical compositions, the thicknesses, and the tensile strength. Grade B is one high carbon steel. Grade C and D, they are stainless steels, and grade A is in between. We have here 2 different thicknesses. Grade A is 0.6 millimeters, and B, C, and D, they are 0.381 millimeters. And they have a relatively high tensile strength, approximately around 2,000 megapascal. For all of our grades, the test specimens were taken from an industrial coil, from the center of the coil, as you can see here. And in both cases, for specimens that we want, they go for testing. And the microstructural characterization samples, the interest is along the rolling direction. So I will start the results with the grade B, C, and D, since we have the same thickness. They are hardened and tempered martensitic microstructures with the prior and austenite grains to be obvious, especially in the grade D. Here, and we have different in type, size, and shape carbides. Carbon B is a carbon steel with a typical cementite carbides. Carbon C, grade C and D, they are martensitic stainless steels with M236C6 chromium-rich carbides. So we did the EBSD analysis in order to have some information about the main microstructural features. There are 3 martensitic lath structures. As we go from grade B to the grade D, we are going from the fine to the coarser martensitic lath structure, and we don't have a strong texture. In that graph, we have the cumulative probability regarding the lath size distributions along the rolling direction for the 3 different grades. On the y-axis, we have the cumulative probability. In the x-axis, we have the size based on the EBSD data that we obtained. So along the line of the 50% probability, we can see that grade B and C, they are very close to each other, and grade D follows a little bit behind. Grade B has the finest martensitic lath structure, and which is depending on the prior austenite grain size, and we know that the finer the microstructure, the better the mechanical properties, thus the fatigue response. Indeed, here is the SN curve for the three different grades. In the y-axis, we have different stress levels, and in the x-axis, we have the logarithmic scale of number of cycles. And grade B has the best overall fatigue strength between the three grades, following by C and then by D. Approximately, we tested 20 specimens for each grade, so we're speaking about 60 fractured specimens. All of them, they were fractured in the waist area, as it was predicted by our FEM stress calculations. Otherwise, usually it was from a surface, but since I haven't marked it, I'm not sure if it was the upper or the lower. I will be honest with you. In all of the grades, we had finite lives up to 10 to the 9 number of cycles. And let's move quickly to the fractography. So I told you, all of the specimens were broken in the waist. And based on the fractured surfaces, it seems that the results are very similar with conventional testing at lower frequencies. So if someone would like to make a clarification between the fractured surfaces, we can split the fractured surfaces for longer life samples and shorter life samples. In the longer life samples, usually we had 1 up to 2 initiation points, usually at the corners or at the surface sites. Regarding the shorter life samples, this area over here, it was very, very common. It was always below the surface, and there are many small initiation points with small crack growth areas very close to each other. And of course, we had smearing because shorter life specimens, higher stresses. A little bit more details about the initiation points. We found different initiation points, starting from the corner or at the edges, and of course some surface initiations. That point, I would like to say that the specimens, they had high tensile strength, so in order to reach until to us, it was cutted by EDM. So probably the corner initiation points and the edge initiation, they are correlated to the EDM process, even though we tried and we polished them, I believe very well. But it seems not so well. But however, we have also surface initiation points correlated to the higher localized stress and or some microstructural features like grain boundaries. In more details, we have seen all the fractured surfaces, and we have found different packages of characteristics for each grade. So grade B, the carbon steel, we have seen triple point initiation similar to that one. There are striations around the initiation point, especially somewhere here, but since you cannot see them, you should trust me. There are some microvoids, like here, which are probably, they are the small carbides that they have been removed during the fracture because they have the same size and shape with the carbides that we had during the microstructural analysis. Based on my experience about the testing, I can say that grade B had a little bit better and more ductile behavior than grade C and D. Regarding the grade C, the number one feature was the slag inclusions. Usually they were aluminum oxides. They were in the fatigue growth region and in the final fracture, but they weren't initiation points. And regarding the grade D, grain facets similar to the SEM photo to the right or the left. It was very common, which is a mark of brittle behavior. And last but not least, we have the grade A. It is of different thickness than the other three. It is a thickness of 0.6 millimeter. BSD analysis gives us the image that the prior austenite grains are bigger and the martensitic glass structure is bigger in that case, and it's okay because it's thicker. We tested it, this thickness, we tested it. We have fatigue data for that as well. You can see a fracture surface of this grade in SEM photo. Here it is very clear how the EDM edge surface, how it looks like, and how the crack, the initiation points are at the edges. But also we have one in the middle. So to sum up, the 20 kHz cantilever bending fatigue test ring can provide experimental results for high and very high cycle fatigue of high strength steep steels of different thicknesses and properties. The EBSD analysis was used in order to have an image about the martensitic glass size, and we saw that the grade B has the finer martensitic structure. The very high cycle fatigue gave us that grade B has the overall best fatigue strength, and that we can have fine laps up to 10 to the 9. And the fractography reveals different initiation points at the maximum tensile stressed area, which was at the same time validating the FEM calculations. We had different types of initiations like corners, surfaces, or grain boundaries, which were correlated either to the process or the microstructure. High number of initiation points, especially when we were in higher stress levels, and grade B reveals a more ductile behavior than grade C and D. Our work was under support of KKS Foundation, and our partners was Voestalpine and Nudeholm. Thank you very much.